development is kind of an active field at the moment. There's been quite a few publications in the last sort of 3-4 months, both from Swansea and other resources. So, yeah.
Right. So when we were asked to speak about, well, how does this research fit within what you see in the department, we thought we could list here these modules here. That is modeling computer systems number 2 with Ferran here. Then the concurrency module where you learn a little bit of a process algebra. Then 275 is the, well, John, how is your TPL called these days? Well, what John and Anton teach these days here.
Hang on, no, I remember. It's automata and something.
Okay. And the main thing is, in order to figure out how this railway verification goes, you need to understand the notion of an automaton. Yeah, so that goes into that. Then Anton teaches the critical systems here, and then Uli is teaching the verification module. And so this is all the stuff that is in the department which directly goes into the railway verification challenge. And this is how it practically looks like. That's what the railway engineers are doing. They draw things which they call a track plan. That's the upper part. And then they write tables, and together, track plan plus tables, they call it a scheme plan. And what we have here is a double junction, and by the way, this double junction has been studied this year by 230 project students. Yeah. And the basic idea is a train can travel here. However, the train can also go down over here, so you can go from the main line to a side line here, or you can travel here on the main line, or you can from the side line come and join this main line. And so that is how these scheme plans look like. And the main thing is you have here these strange things. They are called signals, practically traffic lights just for trains. And what you want is that, for instance, if I want to send a train here over this path here, and I would like to send a train, let's say, down here, then they obviously could collide here or there. And so we want to control these signals with the computer in such a way that the trains cannot collide. And that's the verification challenge. Yeah, so the rail engineers come and draw this plan and say these are the tables. And you computer scientists tell me trains can't collide. Yeah. There are other two properties that they also want to be verified, but this is no collision. That is kind of the main challenge. Yeah. And now you have to ask yourself, well, what can we do? How can we say anything about that? And the answer is, we build a model of this, and we look at the model that it is safe, and if it's safe, then we claim that this design is safe. Yeah? So that is the basic idea, and the question is, how do we build a model? Yeah? The first thing is we need to figure out how this control in the railway actually is realized.
Yeah. So the idea with control the railway is, at the top level, you have some sort of controller, which you can think of as a human being, who sits there with a big panel in front of them and says, I'd like this train to go this way and this train to go this way. Maybe it's automatized sometimes, but usually there's a controller. What he does is he says, okay, I'd like a train to go a certain way, so he makes a route request. Yeah. And then there's this system that sits in the middle called an interlocking, which is responsible for allowing safe requests and denying unsafe requests. So it sits there and it goes, okay, is it safe for this route to be given to this train to travel? If it is, then it will set up the track equipment. So this is like setting signals to green, setting points to be in the right direction, etc. And then, okay, at the bottom we have the trains which observe these signals when they're travelling down the track. Okay, and you also get a feedback the opposite way. So the interlocking will read information from the current track equipment to decide whether it's safe to let a train through or not, and also respond to the controller, yes, I've set the route, or no, I haven't set the route for the train that you wanted. So once you've got this sort of abstract picture, you can move on to the next stage of development, which is to Markus is going to explain. So this one is, the idea is that you use some sort of formal language to describe this model. And for this, one of the languages we use is CSP parallel B. So this is a combination of two languages. One is a process algebra, and one is an event-based or state-based sort of modeling approach. So you take a system, or interlocking, and we split it into different parts. And this is what this picture represents here. So some of it is going to be modeled in CSP, mainly the control aspect, whatever that is. And the reason for this is, okay, the trains and the controller are best suited to a sort of modeling approach which is event-based. So an event occurs in, like the train moving from one track to another, or something like this. And then other parts, such as the interlocking, which was the system we want to check for safety. This is more like a state-based system. You can imagine there's a program that runs, and inside that program there's variables which are changed over time, and this represents a state in our system. Yeah. And this is sort of a new phenomenon. So sort of a double nature of railways. Previously, people had tried to model railways using one approach, all state-based, all event-based, or some different approach. But we sort of pioneered this approach where you put two different specification formalisms together to give a nicer model at the end of the day.
And speaking a little bit about what you have seen in the second year, so the concurrency module, you saw this process algebra called FSP here. That is nothing else but a dialect of CSP here. And what you learned with John Tucker and Anton on automata, B is nothing else than a mechanism to write down finite automata. Yeah? So that is, in some sense, you have now all the foundations for this language there. And here is kind of how the code looks. Yeah? I just want to explain a tiny bit of this here. Yeah? So if I'm a train and I'm in front of a signal that shows to me green, yeah, then I can decide either to move, or maybe as a train driver I see there is unfortunately cattle on the track, then I might want to stay in my position even if I have green. Right? And otherwise, if I have red, I'm supposed to stay. And railway systems are designed in a way that they say, okay, even if a driver drives exactly one track forward, however then stops, then they shall be safe. So the driver is allowed to bring the train to a halt shortly after the signal that he has overlooked. If this is the case, then it should be safe. And that is how we are modeling trains. And this here shows a little bit how this language looks at kind of models the machines, the automata. Yeah. So if someone would like to say, please can I release the following route here, and we want to have a result, we want to have here a yes or a no, then there are a number of conditions that need to be fulfilled. And if all of these conditions are true, then, okay, we are setting the signal associated with the route to red and say, okay, yes, you could do it, and otherwise, sorry, it was a no. Yeah? And so this is how things look like in this hybrid language, and the language construction ensures that these two parts can communicate with each other. And we had a very joyful morning together with our friends in industry reading this kind of code, and they said exactly this is the way how our computers work. So you have the right model. You know? So that was the interesting thing for us. Right. Do you want to take over?
Yeah. So these are the kind of scheme plans that we've been looking at. So you can see this is quite a large scheme plan. It's got lots of sort of points which allow you to switch between different tracks and 4 platforms included in the scheme plan. So yeah, there's some statistics about the track plan there, but the main point is we can actually now verify things like these. So we've come up with techniques on top of what you've just seen, which allow us to sort of break the scheme plan into smaller parts. So if you try to naively throw this scheme plan into some sort of verification tool, then it just won't finish. You could wait a week, 2 weeks, and you won't get a result out because the state space representing the system is simply too large. And so what we've done is develop some techniques which allow verification of these scheme plans, and you can see how things grow. So in the beginning, we can check the first sort of 1,500 states in 10 seconds. And yeah, this grows up to 2 hours when you get to 50,000 plus states. Okay, but what I'm going to move on to show you the process there. So what we've seen so far is a way of sort of modelling using formal languages of a railway system, but we've missed a key part here, and that's the application of these tools. So what we've shown you isn't necessarily understand or usable every day by an engineer who's modelling their track plans. So what we're going to look at now is sort of the tooling side of the theoretical work, which encompasses programming, software engineering, and how are the modules?
Oh, the advanced topics module
The advanced
we had last year.
topics from last year. Okay. So I already said the motivation, so let's get it. What we propose for this is the use of domain-specific languages. So the idea is that if we use a certain form of language, then we can give the engineers something they really want and something they can use to model railway stations. So what is a domain-specific language? Well, you've all seen Java in the undergrad course, and you can think of Java as being so-called general-purpose language. It's like a Swiss Army knife. You can attack pretty much any programming problem with Java. But what you probably don't want to do with the Swiss Army knife is go cutting grass. It's kind of the wrong tool for the job. Or there's some other examples. You probably don't want to cut down trees, and you probably don't want to try shaving. It's pretty risky. So why do we try to do these things with Java in the first place? So at DSL encapsulates this idea. It says, okay, we want to use specific constructs for the domain. So I want signals, I want tracks, I don't want while loops and if statements. Usually this involves trading generality for expressiveness, so I can't write down a while loop in my language if I don't have the while loop construct. I have a signal. What does a signal do? So there's this trade-off. And some examples of this include, well, you've all seen HTML and SQL. These are typical examples of domain-specific languages, and they're quite popular and used quite a lot for what they aim at. So, particular interest of mine is how can we create these DSLs graphically? So we want a scheme plan and we want to be able to draw scheme plans and check properties over them. So for this you can employ something called EMF and GMF. This is a clip-based tool, and it's just a plugin that allows you to develop, as we'd say in a minute, a graphical editor. And from this you can also generate code. So in the traditional sense, lots of people generate Java code. But what we possibly being first to do is to generate specifications or formal specifications from such an editor. So if we have a look at the editor, is that time to show a video? Probably not. Okay, so this is the kind of thing that comes out of show a video.
I think we should try to show a video.
Yeah. If you zoom out. That's fine. So this is the kind of thing that comes out from this development process. So you can see on the right hand side here, you have lots of constructs in the language, or things from the railway domain. So for example, we've got tracks, which are being drawn now, and you can see in the middle there's a point that's being drawn, etc. And you can just drag and drop these from the side and build up a model. And for example, you can put a signal on the track. And then you can say this signal controls entry to this track and forwards. And this can keep going. You can sort of write down properties of the model in this language. And what you get eventually is a generation of a formal specification from this. So this is exactly the code that you were looking at earlier, except it's automatically generated from this kind of diagram. This is much more reasonable for what the railway engineer would like to use every day. And the development process also allows, the development process allows for you to add in sort of validation checks that you generate in the correct model and for what's drawn, etc. So you don't, it's not so much of a leap of faith, oh, I'm just generating some formal model, I have no idea if it's the formal model representing the picture or not. Yeah. Okay, and then this goes on to show that we can go on and verify it using some verification software, which I'll just show at the end. Nice little mouse action to show that we can prove things. So this is proving safety of the model that you see. So what we have is sort of a twofold relationship between the theoretical aspects, where you develop the theory side of things, and the tooling aspects, which need to incorporate this theory side of things, and also remain formal in the sense of the mappings from pictures to sort of formal specifications. And this results in a sort of whole framework, the on-track framework, as we call it, for railway verification. So this is one, user-friendly for engineers, which most verification approaches don't take into account. Two, it allows for abstraction techniques, like we showed the verification results earlier. And overall, what do we get? Well, we get this thing where we can push a button after drawing a scheme plan and say whether it's safe or not. And if it's not, the idea is you get some sort of visual feedback on the track plan why it's not safe. Okay, so maybe I'll just speak a little bit about the impact.
Right. Yeah, so the things that we have been doing, not only this scheme plan modeling, but also some direct code verification, they are actually taken up by Inventors Rail. And the RSSB, this standards organization, they are currently reconsidering the regulations for rail design based on the things that we have been doing. We are by no means kind of, how shall I say, at the end of our work here. Our current proof approaches, which are actually at the moment the best that you can find worldwide. So no one has ever been able to verify a scheme plan of the complexity of Langley before. So in this sense it is quite an achievement. However, at the moment we are only allowing trains to travel on a track in one direction, and we would like to have it, of course, in both. And we know already how this goes. However, we need to develop the analysis techniques. Within Europe, there is a new railway standard coming up, becoming reality. It's called ETCS, and we of course would like to apply our techniques over there. And the last item is maybe the most important one. We do not only want railways which are safe, but we want also loads of trains on the track. And in the UK, the analysis says we do not have enough tracks for the number of trains which we would like to run. We can't build any more tracks because there is no space. You think about London. If you say I would like to build some more tracks, then some houses have to go, right? That would not be very popular, I guess. And so the question is, if we change the design of such a rail node, let's say this double junction, can we get more trains through? And can we prove this? And can we kind of experiment before we come with the building machines and build these nodes? And so capacity analysis is kind of key to all the future developments that are happening there. And in order to do this, we just had yesterday the situation that we applied for an international network for looking exactly on ETCS and capacity analysis, and we just passed the first hurdle, so we have been invited to write a full proposal. And also for tackling ETCS, Swansea is part of a European research bid. You might have heard about Horizon 2020. That is kind of where the European Union puts loads of money into research activities, and we have been invited, thanks to our work, to be part of it. And there are, I think, always some rail projects out. Monica, Anton, Karen and I supervise them regularly. Yeah. And we have also someone just starting with an MRAS actually funded by the company Inventors because they really want this work to keep going. Here, with this, thank you very much.